Bagging is one of the types of ensemble techniques. So here is the bagging algorithm. Bagging philosophy is take multiple bootstrap samples from the population. We know what is a bootstrap sample. Sampling, we take each sample point with replacement again and again. So take multiple bootstrap samples from the population and build a model or build a classifier on each of the samples. So let's say if we take 10 bootstrap samples, we will have 10 models. For the prediction, take the mean or mode, that means take the average or take the voting for all the individual model predictions. So take bootstrap samples, build each model on each of the bootstrap samples. For prediction, take the average or the mode, or that is by voting you choose the final predictor. So bagging has two parts: bootstrap sampling. First you take bootstrap sample, then aggregation of all the learners or aggregation of all the predictions. So that's why bagging is nothing but bootstrap aggregation. So bootstrap aggregating, so it is defined from, or it is the name is in fact defined from bootstrap aggregating. Bagging, we combine many unstable models. I will not say unstable, many of the moderately good models to produce one stable model, one final model. Hence the predictors will be very reliable, that is less variance in the final model. The coefficients will be highly consistent. So first step, bootstrapping. If we have a training data set of size n, then we draw samples with replacement of size n. That means we take a single data point, we note it down and put it back. Again we take another data point, we note it down and put it back. We repeat this process until the number of samples in the whole data set. So number of size of the whole data set. If the training data has a size of n, then we take sample 1, that is bootstrap sample 1. There we will do the sampling n times. So we will draw a random sample with replacement of size n. That gives a new data set. Then it will be repeated. I mean, each of these bootstrap sample might have can contain repeated observations, or some of the samples might not even contain some of the observations from the whole training data set. So we are selecting records one at a time, returning each of the selected record. We'll select one record. This has 1, 2 and so on n records. So we'll select a record randomly, we'll keep it here, and then we just note it down and put it back. Again we select. Next time we might select the same one or a different one. Again we repeat that process n times. That will form bootstrap sample of size n, that is bootstrap sample 1. So we create b such new data sets 1, 2, 3 and b such. These are called bootstrap samples. This is bootstrap part of bagging. Here is the bagging algorithm. You have the training data set, you draw bootstrap 1, bootstrap 2 and bootstrap k bootstrap samples. So training data set D, draw k bootstrap samples. We know how to draw the bootstrap samples. Each of the data set size is n, then bootstrap sample size will also be n, and then there will be k sets of bootstrap samples. Each of the bootstrap samples build a model m1, m2 and so on, mk models. So build a classifier mi on each of the bootstrap samples. Then we will have total k classifiers, because there are k sets of bootstrap samples. We have k models. Then either vote over or take an average, or whatever is the best way of aggregating, we can aggregate it. Or for now we will take a vote over to find the final prediction. So vote over for the final classifier output, or if it is regression then we can take average. Then that will be the final bagged model. So we take k bootstrap sample sets, we build k models on each of these, and all these models are combined together. Consolidated model is bagged model. Why bagging works? Similarly, the way we discussed why ensemble works, in fact bagging is also a typical ensemble model only. For any ensemble model, The only thing that we need to make sure that is all the samples, all the models need to be independent. So we are selecting records one at a time, returning each of the selected record back in the population and giving it a chance to be selected again. So note that the variance of consolidated prediction is reduced if we have independent samples. So that is why we can reduce unavoidable errors made by single model. So if we have one single model, it might capture some kind of pattern or an outlier which we might not want. But if we are drawing bootstrap samples again and again, then we might have a very consistent, robust model at the end of the bagging. In a given bootstrap sample, some observations have chance to select multiple times. Some observations might not have selected at all. That we know because we are doing sampling with replacement. There is a proven theory that bootstrap sample have only 63% of overall population. Rest 37% is not present. That means each of the set 1 and set 2 might not have a lot of observations in common. So the data used in each of these models is not exactly the same. Maximum it will be 63% same. This makes our learning models independent. I built model M1 on a different data set, M2 on a different data set. Again, they are sampled from a real population, the original population that we are taking from. So the models are fairly independent. Once the models are independent and the models are finally aggregated, so we will get a better model. So finally the errors from individual models, they cancel out and give a better model, that is the ensemble model with higher accuracy. Bagging is a really useful when there is a lot of variance in our data, when there are too many points that are away from rest of the point, when there are too many outliers. Maybe bagging is the way to go. We take bootstrap samples and build several models and then finally combine them to build a bagging model. Let's see an example how we build a bagging model. Let's do an example to understand the bagging models. The dataset that we are going to consider is Boston housing price data. This is one of the most famous datasets that is used in machine learning. Now it is part of mass package in R. We need to import it from mass package, or we can import it from our datasets library as well. Get some basic meta details of the data. How many rows are there, how many columns, what is the structure of the data. Take 80% use that as training data, and then remaining 20% should be used as holdout data. That is okay. Build a single linear model on the training data. Then on the holdout data we will see what is the error, that is the squared deviation. What we'll do later is we'll build a bagging model with at least 25 models. That means we have to do a bagging, that means bootstrap samples need to be minimum 25. We'll build a bagging model. On that bagging model, on the holdout data, we will again see what is the error. Then we will see what is the improvement in the error. So let's do an exercise. Let me clear off my window here. Library mass needs to be installed. I have already installed it. Within mass you can find Boston dataset. This is the Boston dataset. The number of rows are 506, number of columns are 14. This is the structure of Boston dataset, MEDV. So this is about house pricing, house prices within Boston area, and this is the final price, and there are several other fields that will decide or that will highly impact the price. You can find out the details of Boston dataset anywhere on the net, and this is the actual dataset. This is how it looks like. These are some of the indicators that will actually impact the final price of a house. We are predicting the final price of a house. This is a continuous variable. We are going to build regression model. As part 1, what we will do is we will take 80% of the data randomly and make it as Training data remaining 20% need to be kept as test data. So we are using Carrot library to make the data partitions. We first made the sample seed, and now we will take the data partition. This is training data, this is test data. So on the training data we can see how many rows and how many columns are there. So on the training data there are 407 rows, 14 columns. Similarly on the test data, remaining rows will be there, 99 rows. Overall there are 506 rows, as we can see in the Boston data. Now the next item, that is building a simple linear regression model on the training data. So we have training data and test data. We will build a usual linear model on the training data. This is the summary of the model. We have an R square of 72%. Some are insignificant, some are significant variables. With that model itself directly, what is the accuracy on the holdout data? We'll try to see what is the testing accuracy, so or the error on the holdout data is 1488. That is, the squared error is 1488. So this is the error. Now when we build the bagging model, we expect lesser error, lesser sum of squares of errors. So to build the bagging model, we need a library called ipred. So if you don't have the library, you need to install it. Then we need to build a model, bagging model, using bagging function, mudv versus rest of the variables. Train Boston is the data set, number of bagging, like this is ensemble model, number of booster samples that we want to draw so that we can build number of bagging models. So 50 is the number of models that we want to build. So this is the bagging model that we are building. So there are 50 bootstrap replications, or 50 models have been built. Then based on that we will do prediction. Then we will calculate sum of squares of errors, and the error happened to be 1125, whereas earlier the regression error was 1498. Definitely there is some improvement. In fact, when we repeat the bagging again, we might see slightly lesser error or more error, but again we can do one more iteration of bagging, one more iteration of bringing 50 samples again. This time error is 1130, slightly higher. Again we will do that. This time error is 1165, 1164, 1159. So obviously we can believe that the error is around 1153. Error is around 1150. So what is the improvement in the error? Here the improvement error is 22%. You can see there's a 22% improvement in the accuracy, or the error is reduced by 22%, because the bagging error is 22% lesser than the actual regression error. That is how bagging works. Random forest. Random forest is a specific case of ensembling technique. Within that, a specific case of bagging methodology. Bagging specifically on decision trees is the random forest. Like many trees form a forest, many decision tree models together, bagged together, is a random forest model. Let us see the algorithm of random forest. In random forest we include two types of randomness. Earlier in bagging, what did we do? We picked samples, we bootstrapped samples, set of k samples, then we built k models. Now in random forest we take bootstrap samples of the population and build decision trees on each of the sample. So we take bootstrap samples and start building decision trees on each of the sample. But the trick or the major point in random forest is, while building the individual trees on the bootstrap samples, so that means while building the individual models, we induce one more set of randomness by choosing a subset of the features. We will not build the models on each of the samples using all the features. We don't use all the predictor variables. We don't use all the variables that are impacting. We use a random set of variables. So that model might not be one of the best model, but at least it will use few variables and give us a loose classifier. So that is the major point in random forest, that we will be using a subset of variables. Why are we using subset of variables? So that if we use one subset in model 1, another subset of variables in model 2, another sample of variables I'm talking about, another sample of features in model 3, then there will be these all models will be, all the trees will be totally independent, and each tree will be giving us a different result, but all of these trees together might give us a good consolidated random forest model. Random forests are very stable and they are as good as SVMs, and sometimes they are better than other algorithms. They work like really very good. So once again, the overall random forest algorithm very close to bagging. Let's try to understand that. The training data set D has number of features. Let's say there are T number of features in training data set D. So there are T number of features, and then draw a K sets of bootstrap samples. So this is bootstrap sample 1, 2, 3 and so on. There are K sets of bootstrap samples. Okay, for each bootstrap sample, earlier in bagging we started directly building the model, but here what we'll do is we will again draw another sample, that is we will build a decision tree on this bootstrap sample by using only P1 number of features or P number of features, where P is much less than T. So T is overall number of features, T is overall number of predictor variables, P is only subset of that, randomly chosen subset. If there are 200 variables, maybe we will choose only 30 or only 50, or randomly selected 100 variables we will use and build decision tree model 1. Here we will come to this point. B2, again a bootstrap sample which is independent of B1, so B1 B2 are independent. P2, again another subset, maybe it is just 30 variables but not necessarily same as this 30, randomly chosen again from T. So we have randomness induced here, randomness induced here, then we will build a decision tree model 2. Like that, we on every bootstrap sample we take a subset of features, then we build a model D1, D2, D3, D4 and so on dk. Finally we consolidate them as random forest model. How do we do consolidation? Maybe by voting, while predicting. If this predicts as 1, 1, 1, most of them are 1 and one of them is predicting as -1, by voting we give the prediction as +1. So that way we consolidate and find the build the random forest model. So once again, the algorithm: training data set D with T number of features, draw K sets of bootstrap samples. For each bootstrap sample I, build a decision tree model MI using only P number of features, where P is much less than T. Each tree has maximal length and they are fully grown, not pruned. Each tree is like overfed and overly grown, because anyway we are taking less number of features. There is no problem of overfitting anyway, because we, instead of taking all the variables, we are taking a subset of variables, so we can grow the tree as much as we can. Each tree is doing very good job of at least classifying a given set of variables. Then we will take total K decision trees, because there are K sets of bootstrap samples. Each of these are built on relatively different training data sets and different sets of features. Different training data sets because they are bootstrap samples, different training features. Now finally vote over, based on voting we will consolidate and have the random forest model. So random forest model is nothing but we have all these models together, consolidation is done based on the voting. Finally, if it is regression, then we'll take the average of all the outputs, that is the regression consolidation. If it is classification, we take vote and the one, let's say if we are predicting +1 and -1, if there are 30 trees, then 25 trees are predicting as +1. Based on voting we will say the final prediction is +1. That is the random forest algorithm. The randomness in random forest is the major technique or major point that we need to once again look into. The random factors in random forest. We need to note the most important aspect of random forest, that is including the randomness into bagging of trees. There are two major sources of randomness, that is randomness in the data, that is done by using bootstrapping. This will make sure that any two samples in the data is they are somewhat different. Randomness in features. While building the decision trees on bootstrapped samples, we consider random subset of features, so we have definitely ensured that all the trees are random. Why to include randomness? We always knew that major trick of ensemble models is independence. If we take the same data and build the model 100 times, it is not going to improve us, if it is not going to give us an improved model. To make our decision trees independent, we take independent sample set and independent feature set. Generally, a rule of thumb that we can consider, that is square root of number of features if the number of features are high, or if the t is very large, not very large, then we can put t by 3, that is 1/3 of the features. Now, why this random forest works? What is the technique? Based on ensemble only it will work. Then we will see one more demo where it shows why this random forest methodology really works. For a training data of 20 features, we are building 100 decision trees with 5 features each. Let us suppose this scenario. A training data has 20 features and we are building 100 decision trees. That means we built 100 models, but each of the model has only 5 features each. Instead of single grade decision tree, the individual may be weak classifiers, because instead of considering 20 features, we are considering only 5 features in each of the tree while building it. It's like building weak classifiers on subsets of data. The grouping of large sets of random trees generally produces accurate model. Now we have 100 trees. Each one of them is doing one thing very clearly. Maybe a one good classifier for a particular pattern. Each one of them is finding out one. Each one of them is good at classifying one particular pattern. All of them together are making a good random forest model. In this example, we have 3 classifiers, M1, M2, M3. M1 classifies anything above the line as +1 and anything below the line as -1. So M1, if you see, this is classified as, let's say, +1. Everything below it is classified as -1. So here it is doing the right thing, but this M1 is doing wrong in terms of this. M1 is wrongly predicting this, M1 is wrongly predicting this. Whereas M2 is classifies all the points above the line as -1, below as +1. This is M2, all the points above the line as -1, all the points below the line as +1. So this is M1. Okay, this is the M1 model. So anything below the line, above the line as +1. So this is +1, +1. This is wrongly classified by M1. This is anything below the line as -1. So this is classified wrongly by M1. Now this is line M2. Anything above this is classified as +1. Anything below this as -1. So M2 is wrongly classifying these two classes. This is M3 model. Anything left hand side is -1, anything on the right hand side is +1. It is so wrongly classifying this and this as wrong. So each of the model are very weak in all of the cases, but all these 3 weak models together make a very strong model. If we take all these boundaries, anything inside the boundaries is -1, anything outside the boundary is +1. So that way the model that consolidated based on these 3 models is the best one. It has almost 0 error. It is not wrongly classifying anything. So let's see an example of random forest. Now let us see an example of random forest. So we will download a data set called car accidents IoT data. in that there are many variables, and then the output variable, whether there was an accident or not, and there is rest of the predictor variables are sensors in the car. Build a decision tree model to predict the fatality of the accident, and then build a decision tree on the training data. So building the decision tree model is our final objective. First, what we'll do two steps. First, we will build a usual decision tree, one best decision tree that we can build on the training data, and then we will see its performance on the test data. That is step one, with using one decision tree. Then we will build a random forest model with multiple decision trees consolidated together. Then on the test data, we see what is the performance of random forest model on the test data. What is the improvement and all that we will try to observe. So here is the data set: training data and test data, car accidents, IoT. So IoT data, Internet of Things, you have many sensors in the car, some sensor near the steering and the wheels, some sensors near the bumper, based on some sensors near the clutch, etc. Based on all these sensors data, we can predict the fatality of the accident. So how many variables are there in the train data? There are 23 variables and 15,000 observations are there. In the test data also there are 9,000 observations, 23 variables again. So the output is fatal or not fatal. So let's see, in the training data, the data set looks like this: sensor 1, sensor 2, and so on, sensor 22, and the fatality 1 or 0. This is the output. Now we'll try to build a decision tree model, that is car fatality versus rest all the variables, and minimum split size 30, CP 0.03, some standard values we are taking, and the data set is training data set. So this is the tree that we are building. This is the tree that we have built, and let us see on this tree what is the accuracy statistic. The accuracy is 82%. Most of the times it is predicting correctly. That is testing accuracy, training accuracy. On the testing data, what is the accuracy? We will again run it on the testing data. On the testing data it is 82%. On the training data it is again 82.85. On the testing data it is 82.84. So fairly good model, decision tree. We will build a random forest model. What we'll do is we'll build 200 such models, but every time we take bootstrap samples, as well as the number of features that we are considering is just by 3, number of columns in the train, that is number of features divided by 3. So we are taking 1/3 of overall features. So there are, the number of features are around 25. So every time there are 25 features, as we can see, 23 features. Every time we will be taking somewhat around 7 or 8 features in each of the tree, and we will build 200 such trees and consolidate them to find to make a final random forest. So this is the random forest model. It will take some time because we are building 200 trees in a go. So random forest model just built. We can see the summary of the random forest model. This is the summary of the random forest model. Majorly it will give ensemble or bagging type of summary. The one that we want to see is maybe the confusion matrix or the final tree, the forest. We can actually look at the random forest as well. Very hard to make sense out of this data because there are 200 trees that we have built. We'll go ahead and find the training time accuracy, that is in time accuracy 93%, much higher than earlier data set, that earlier model which has 84% accuracy. Now testing accuracy on the holdout data is 93.45. so random forest gave us much better, much more improved model classifier compared to a single decision tree.